All right, dear students, Assalamu alaikum. Let's discuss a very fundamental sort of problem which few students are facing regarding the potential difference between 2 points A and B in the field of a point charge and in the field of a line charge. So both the charge distributions are very fundamental and yet simple, and they are also important. All right, so generally speaking, the potential difference between 2 points A and B is given by this expression. All right, and where the point B is the initial point and point A is the final point at which a unit positive jet charge is placed from this point to that point in the field of some charge distribution. So let's say if we have got a point charge Q, right? So the best way to analyze such charge distribution is to keep this charge at the origin of a spherical coordinate system. So if we would do so, then the position vectors locating point B and point A would nothing but the radius of these spheres given by the length of these arrows, or we know that the coordinates of a spherical coordinate system are r, theta and phi. So if we would place the source charge at origin of a spherical coordinate system, then the first coordinate, that is r, would be the position, would represent the sphere on which the point charges or the points, field points would be located. If this is the case, then the potential difference formula from here, it can be converted down to this relatively simple formula, where there is no integration involved, where this RA and RB are nothing but the radii of the spheres over which these field points A and B are located respectively. And those spheres are, by the way, centered at origin as well, as the origin also contains the source charge Q. All right, so this is a potential formula for potential difference between 2 points A and B in the field of a point charge Q located at the sphere, at the center of this spherical coordinate system. But if you want to know the potential, the absolute potential at any point within the field of the same point charge located at the origin of a spherical coordinate system, in that case we know that the initial point should be at some reference point over which the potential is 0. The absolute potential of the point B should be 0, and we discussed that theoretically this point is something at infinity. So to keep this point at infinity, to keep the initial point at infinity, to put the initial point at infinity, definitely the distance of the that field point B from origin, which is RB, should be infinity as well. If we would do so, this reciprocal will be 0, and this potential difference expression would be converted down to absolute potential expression. All right, so now collection of all points over which the potential is the constant, we all know, is nothing but equipotential surface. So in this expression we know that Q is constant because it is the source charge located at origin. 4 pi epsilon naught is definitely constant. The only variable thing is this field point. If we and this field point is given by the distance between the origin and the field point. So a collection of all those points which are equidistant with respect to origin would give us the same potential, and we know that this in a spherical coordinate system it is nothing but a sphere. All right, so a sphere is the surface which is equidistant with respect to the origin. So keeping RA constant in spherical coordinate system in this particular scenario will give us a sphere which is also an equipotential surface. Move at any point on that surface, the work done would be 0 or the potential would be the same, and same goes for every sphere which is equidistant from the source charge. In this particular case, which is equidistant from the origin, or which has got a constant value of first of the three coordinates of a spherical coordinate system. That is the radius of this sphere. In this particular case, the potential difference is given by this formula, and absolute potential is given by this formula. All right, and if we would put R equals to constant, RA equals to constant in this particular setup, where the source charge is placed at the origin of a spherical coordinate system, in that particular case, keeping this value constant gives us equipotential surfaces which are spheres. Okay, which are spheres. And this RA is by the way, in this particular case, is the distance between the source charge and the field point A, and RB is the distance between the source charge and the field point B. But what if the source charge is not located at the center of the spherical coordinate system? Would we be able to use these formula? The answer is no. Definitely this source charge Q will form a field exactly this, like this one, but the mathematical representation would now change because we don't have spherical symmetry now. And let's say in this setup of charge distribution, we have a point here, point A, and point here, point B. All right, and now we want to find the potential difference between these 2 points when the source distribution is only a point charge, just like that one. But now the point charge has been removed from the center of a spherical coordinate system to some arbitrary point. So let that arbitrary point Q be x prime, y prime, z prime. So the vector locating the field point, locating the source point, sorry, would be x prime ax plus y prime ay plus z prime az. We are talking about position vector which is locating the charge Q, is given by this. All right, and the position vector locating the point A and B, let's say the point A is x1, y1, z1, the coordinates are such that, and the coordinates of point B is x2, y2, and z2. If that's the case, now the position vector locating point A is given by x1 ax plus y1 ay plus z1 az, and the position vector locating point B is given by x2 ax plus y2 ay plus z2 az. But mind it, these RA and RB are not the same as these RAs and RBs were, because now the origin, the reference point has been shifted, the source has been shifted. So according to this formula, if you want to use this formula, really, so we'll have to actually replace, in place of RA, the distance between the source point and the field point A, and in place of RB, the distance between the source point and the field point B. So what we really need to know is this RA and this RB. RB. The magnitude of these vectors RA and RB, capital RA and capital RB, would give us the required entities which will replace here to find the potential difference between the 2 points. So for what we know is this position vector, which is R prime, and what we know is this position vector, which is let me write it here, RA, and this position vector, which is RB. So what we really know is this RA and RB. But once we know R prime and RA, we can simply calculate RA, capital RA, to be RA minus R prime, head to tail rule. And for RB, RB minus R prime. Okay. This is something you can find pretty easily if these coordinates of these points and coordinates of the source point are given to you. So these are the things which you can find pretty easily. Okay, so x1 minus x prime ax plus y1 minus y prime ay plus z1 minus z prime az. And similarly, x2 minus x prime ax plus y2 minus y prime ay plus z2 minus z prime az. I hope I'm clear so far. So now in place of this RA, this formula which was valid for this expression, this arrangement, RA was the distance between the source point and the field point A, and RB was the distance between the source point and the field point B. So here, this was the source point Q, and this was the field point A, and this was the field point B. So the magnitude of RA would give us the distance between the field point and the source point. All right, so this is what we would evaluate. RA magnitude is given by x1 minus x prime square plus y1 minus y prime square plus z1 minus z prime square. Similarly, RB magnitude is given by x2 minus x prime whole square plus y2 minus y prime whole square plus z2 minus z prime whole square. So now these magnitudes are the one which you will calculate first and then replace it over here. So over here we'll have to replace the magnitude of RA, and over here we'll have to replace the magnitude of capital RB, generally if the source point is not located at the spherical coordinate origin of the spherical coordinate system. All right. So now the equipotential surface around this charge distribution would be again spheres which are centered at the point charge q, just like that one. But in that particular case, the equipotential equation for equipotential surfaces were pretty straightforward. R is equals to RA, or R is equals to RB, or for that matter R is equals to any constant is valid for this particular charge distribution or arrangement of the charge distribution. But for this arrangement, we cannot simply give the equipotential surface expression in this fashion. Okay. So I hope I have made the whole scenario clear to you all, that if a point charge is given to you and how to find the potential difference in absolute potential and that charge distribution. If you have the liberty, if there is only one point charge, so the best way is to keep that point charge at the origin of the spherical coordinate system. But if there are more than one point charges or other charge distribution, or if it is explicitly told to you that the charge is placed somewhere off origin, in that case you cannot use this formula directly, RA and RB. Here you'll have to do some maths in order to find the distance between the field point and the source point first before replacing it over here. All right, so these RA and RB in this case are nothing but the first of the three coordinates of a spherical coordinate system. But here, when we are not able to exploit this symmetry, in that case we'll have to do some maths, and the RAs and RBs here in this case, the one in which there is no symmetry, are the position vectors locating the field points. So these are not magnitude of these are not the entities which we have to replace here. So this is something we should be aware of. What we have to do is actually the magnitude which we have to calculate here are not these magnitudes, rather they are the magnitude or the distances between the field point Q and the source point Q and the field point A and B respectively. Hope I've made things clear to you all.